Alrighty, welcome back. Getting back to our linear algebra topics of systems of linear equations, one of the running themes for the course. So today we're going to do a bit of a recap of some of the linear systems and take it one step further with the linear transformation lens that we now have. So let's just walk through that step by step here. So one of the things that's going to come up in engineering work, anything that's large scale, there's going to be matrices representing properties of materials, things like that. And a lot of it's going to boil down to solving systems of linear equations, sometimes 10,000 by 10,000. So we're looking for the theory that underpins that. And one of the big questions is, does this system have a solution? And if so, is it one solution or is it an infinite number? And we talked about that sort of a few weeks ago now. Well, what we've learned is that we can certainly solve these by hand faster if we represent this as an augmented matrix of coefficients. And these are the same thing. There is no difference between writing it out the long way or writing it as an augmented matrix. They're the same system. We interpret it the same way. We just associate each of the columns with one of the variables, and they're the same thing. All right. Then we had the other lens, just thinking of vectors and linear independence back in that section of the course, where we had this right-hand side, and if we think about sort of column vectors here, we had, not x that. If I think of the multipliers for x here, we had 1, 0, 2, all times x. Oh, well then we can talk about 1, 0, 2, x. Plus 1, negative 2, 0, y, plus 2, negative 1, 3, z equals negative 3, 2, negative 4. And if we're trying to solve that system of equations, we can rephrase that as asking, is the vector negative 3, 2, negative 4 in the span of those three other vectors, 1, 0, 2, 1, negative 2, 0, 2, negative 1, 3. That question, let me phrase it this way. That question is identical to the question of, does the system of equations have a solution? Question mark here as well. There we go. Very quiet. Because, well, knowing what we know now about span, well, span is the vectors I can build by taking linear combinations of those three building blocks. And we're asking, out of all the linear combinations I can I make that negative 3, 2, 1, negative 4 vector? If the answer is yes, then there's a solution. I can find an x, y, and z that make this whole thing work, and that's the same as going back to our original equations, finding an x, y, z that is a solution to our system of equations. So now we're talking about vectors in R3 all of a sudden when that wasn't in our playbook before, if we were just looking at this version of the system. That didn't look like vectors. Now we can think of it as vectors. But that's not all. We can also now think of it in terms of a transform. So let's take this left-hand side here and call it the matrix A based on the transform L. And, well, wait a minute. If that's my transform, and I'm trying to get it to map to here, we are asking is, let's do it this way. Another way to do this is to ask, is the vector negative 3 to negative 4 in the image of L, or we might also say, or in the image of the matrix. We often talk about the matrix being a standalone thing. The standard matrix associated with L, and that's going to be, again, equivalent to, does the system of equations have a solution? That's new. But the idea is there some x, y, z I can run through this transform and get negative 3 to negative 4? If there is, well, that means I map to the point outside in the output, and that's the image. The points I can reach with the transform are the image. All right. And then we get into the fun stuff. Dimension of kernel, dimension of image here, and how that correlates back to the original system of equations. So if we take a quick look at this matrix here, that's the original. What we learned last class was it's a lot easier to figure out what's going on in a linear transform if we reduced it to reduced row echelon form, RREF. And what features are we mostly looking for in the RREF? Yep. Columns leading ones and columns without leading ones, exactly. So we have two columns with leading ones, and we have one column without. One column without a leading one. Perfect. And one of the things we learned from that little analysis was if there's a leading one here, we can take a look at those two vectors. They're going to be linearly independent. These two columns here are linearly independent. They point in totally different directions. One's the x-axis vector, one's the y-axis vector. And perhaps not as obviously, that means the two vectors over here are also linearly independent in the original matrix. That was one of our insights. So what that meant was these two vectors here are going to be a basis for, sorry, keep the red color here. Those two vectors there are going to be a basis for the image of L. So the things I can reach, the things I can map to with this matrix part here, as linear, thinking about it as a linear transform, I can get some linear combination of those two things. Those are two columns. Those two columns are a basis. And if I have two vectors in my basis, then my basis is two-dimensional, or my space is two-dimensional. So the image is two-dimensional. And we can get the kernel in two different ways, but the obvious way is there's one column that did not have a leading one, and so that gives us the dimension of the kernel. Dimension of the kernel is one-dimensional. The kernel was a little more complicated to work with, to calculate, but we could easily, from the RREF, get its size anyway. Any column that does not have a leading one, that contributed a free variable to the kernel. There's a whole bunch. There's a whole thing yesterday. Take a look at yesterday's notes, though, if you want to go over that in more detail. But the upshot is we can immediately get these kinds of things here, and we have this lovely consequence. Once we look at this RREF, first of all, is there a solution at all to this system of equations? Take a look at it. We're going to do a quick show of hands, yes or no. Does the system of equations have at least one solution? Show of hands for yes. Perfect. Show of hands for no. Fantastic. Right. So the 0, 0, 0s don't matter, but we have what would have been a red flag would have been 0, 0, 0, something, 1, for instance. That would have been no solutions. We don't see that, so we're good. So there is a solution. And the question is it a single solution or an infinite number? We can answer that also, because if there's a single solution, that means our function was injective. And one of the criteria for a function being injective was that the kernel of L is only equal to the 0 vector. We can apply a little logic here. Wait, so if the kernel is only the 0 vector, our kernel is one-dimensional. Is the kernel just the 0 vector, yes or no? No. I got a whole dimension to play with. There's going to be some line in 3 space. Yeah, we're working 3 space. There's going to be a whole line of points that all map to the 0 vector. So that's not true for us. This is violated because our kernel of L is one-dimensional. This is the 0-dimensional set. So if it was this, we'd have a 0-dimensional kernel. We don't have that. And so that means we don't have a single solution. We are down to one possibility left, which is that there's an infinite number of solutions to this system of equations. Boom, boom, boom. And it's, I don't know, not easy to express, but it's a straightforward logical chain now that we have this linear transform thought process and matrix versions.
Really,
Please. Yeah.
Why does having a single solution mean that L is injective?
Right. What? Yeah. So there is a jump there. You're absolutely right. If L is injective, if you think about what we're actually mapping here as a transform, we'd be taking this 1, 1, 2, 0, minus 2, minus 1, 2, 0, 3, multiplying it by x, y, z, and getting negative 3, 2, negative 4. That's another way to write it. So usually we've been doing this. Did that answer the question? Oh, perfect. Okay, good. I was going to go on for a little bit longer, but that's perfect. Yeah, so only, yeah, I'll stop there. Any other questions, especially about this chain of logic? Sort of building up these properties of linear transforms and going, hey, what does that mean for this new question about systems of linear equations? Please.
So it can only be either a single solution or no solutions or an infinite number. Like you can never have 3 solutions or 2 solutions.
That's right. I think about week 5 or so, we did that analysis of systems of linear equations, and these are the 3 options you get, because the solutions are a subspace of the input space. And actually, we can see that here. The solutions are things that I can use for x, y, z that map to this point. It's going to be a subspace. It's a system of equations, and subspaces are infinite. You never get 2 points in a subspace because of that closure under addition, scalar multiplication. Again, more consequences from like week 2 play out here. All right. Any last follow-ups on that before we change gears a little bit? Actually, sorry, before we summarize it? All right, let's summarize it. So we are now going to look at this system here, this augmented system. We didn't do that with most of the transforms before. We just focused on the A part. But we're going to treat that A part as the standard matrix for some transform L. And it's linear. Every matrix represents a linear transform. Transform L. All right. And again, there's those 3 choices. We have no solution, and that would be this case here. We have no solution here. I think I have some other things I want to say about this. I just want to make sure I don't forget anything crucial. Nope, that's about it. All right, so again, the B we're talking about here is this right-hand side of the equation. So in this case here, if B is not in the image of A, then the system of equations has no solution. I literally cannot make this right-hand side vector by transforming the columns of the left-hand side. I can't reach it. It's not part of the image. And the consequence is that there's no solution. This part here, the kernel of A equaling just the 0 vector, and I'm going to emphasize here, just the 0 vector, that, as we said, means that L is injective. B being in the image of A means there is a solution. There, and let's be clear here, there's at least one solution. And if we add those 2 together, we get that the solutions are unique. Those together mean the system of equations has exactly one solution. And then we go to the third one, which is the obvious third option. We had the same right-hand side, our B vector here, is in the image of A. I can reach this B vector with this linear transform. That means when we think about the system of equations, there is at least one solution. There is at least one solution. I at there twice, not having. At least one solution. And this means, so the kernel is larger. We can't get any smaller than just the 1 point. So if we say it's not the 0 vector, it's larger than just the 0 vector. Then we add that to L is not injective. That means that multiple points are going to get to my B vector here. A whole bunch of points over here are all going to map to B. And a consequence of that is that it's not just some random set. It's not just a couple of vectors. The linearity, the linear independence, all those other things come into play, and we add up those two conditions. It means that our system of equations will actually have an infinite number of solutions. Number of solutions. And that's our big classification of the three types of systems of linear equations. Through the lens of linear transforms. Please.
You have kernel of A doesn't equal.
Yeah.
Something that is larger than, so does it also possibly include the zero vector in the larger?
Yeah, I was trying to find a nicer way to say this. So the zero vector is always in the kernel because one of the features of a linear transform is 0 always maps to 0. Otherwise, you don't look at the linearity. So 0 is always in it, but I didn't want to say, I guess technically, I didn't want to say this because our like set notation, it includes the zero vector but is bigger. We didn't have that notation for this plus more. So the closest I could get was the not equals with what we had. But implicitly, it has to have the zero vector as well as some other stuff if it's not equal to the zero vector. So yeah, go by this. The kernel is larger just than the zero vector is the more clear statement.
And then for the last case, it's also, so the function can either be surjective or neither injective or surjective.
Correct. Yes, we're saying it's not injective, but that still leaves surjective on the table, possibly. Yes. Or neither, yeah, absolutely. Fortunately, the surjective doesn't affect this. It doesn't come into play. It comes into play a little bit later, but not for solving the systems of linear equations, that solution space. Super exciting, right? No, it's not. All right, so that's fine. Let's get on to something that's more practical. So one of the things that engineers do all the time is they formulate structures, they come up with equations, and they represent them as matrices, and then we often combine them through what is called matrix multiplication. This is the vanilla thing. Second-year mechanical engineers are doing this by about week 3 of second year, just doing large-scale matrix multiplications in Python. So the idea here is that if we have linear transforms, we often apply them one after the other. We do something, then we do something else, then we do something else. That's a chain of transformations. The way that's going to work, the way we're going to implement that, is through matrix multiplication. As an example, it turns out that rotations are rotations are linear transforms. If I rotate things, it satisfies the plus operator being order independent. Same thing for scalar multiplication. They're linear transforms. And what that means is, if we talk about rotations and I want to do two things, imagine just walking around in any kind of graphics, gaming, 3D gaming environment, you are going to turn your camera, something's going to move in front of you, you're going to need to compose those operations together. And you can imagine if we start with this yellow block and then we rotate around the x-axis is here, so we flip it down 45 degrees, and then we rotate that around the z-axis, so we rotate around the center vertical here. We're going to take that gray and rotate it into the red. I would like to be able to do that very quickly, and we'd like to know how we can do that maybe all in one step. The way we're going to do that is we're going to compose our matrices. But the general case first. All right. Imagine we have a sequence of transforms, L1 from Rn, so Rn, with L1 to Rm. Then we have a second transform which key has the same input space as L1's output space. The output, L1 output, is equal to the L2 input, which sort of makes sense. If L2 is waiting for a certain kind of input, we have to give it that, or it doesn't make any sense. But what we can do with that is then we can map that space with L2 to some third dimensionality. All right. I'm sorry, I think I've misplaced my order here. That's the sketch of what's happening here. We're taking some vector in 3 dimensions, mapping it to a 2-dimensional thing, but my second transform loves 2-dimensional inputs, so we can transform that into some 5-dimensional output. Sure, whatever. The translation of this little circle here is L2 follows L1, or is applied afterwards, or L2 of L1 of some vector v, is what we mean by that circle thing. The order is L1 gets applied first, and then L2. L1's on the inside of the brackets, and then L2 is on the outside. I always find that counterintuitive for some reason myself, so I emphasize it more for my sake, maybe than for yours. All right, so this is the thing we want to do. Again, this is the rotation. This could have been R3 and R3 and R3. This is rotate around the x-axis. This is rotate around the z-axis. Hey, we can do that all together in one transform of L2 following L1 all in one step, in principle. All right. Now, can we do this? Well, first we should know whether that composed transformation is in fact linear. And zero shock here, it absolutely is, but we haven't talked about linear transforms and their definition in a while, so this is good practice. So we have these two maps, and they're both linear, and we want to show that L2 following L1 is also linear. For that, we need the criteria for a linear transform. That is a relatively short list of just 2 things. If a function is linear, this side, what's one of the criteria? Please, yep.
Closed under addition?
Oh, close. We don't phrase it that way. It's about addition, but that's the vector space one. Linear transforms, it's in that flavor, but slightly different. Yeah, please.
We have L1 of V and L2 of W. L1 of V plus L2 of W is the same as L1 of V plus W.
Perfect. I'm going to use V1 and V2, but absolutely what you said there, yeah. So if we have 2 vectors and we add them first, we can do that, and we'll get the same thing if we transform them first and then add them second. So it feels like closed under addition, but yeah, the technology, the equation's a little bit different. What's the other one from the side? Please, yeah.
If you like multiply the vector and then apply the linear transformation, you can just move the scalar multiplier outside of it.
Perfect. If you have a scalar multiplier inside, you can move it outside and get the same thing. Perfect. Those are our 2 criteria. So let's check those for L2 following L1. Check for L2 following L1, which is the same thing as L2 of L1 of V for any V. All right. Be specific here, V and Rn. So we're going to go all the way back to the start. Whatever L1 takes in, that's going to be our starting element for all these things. All right. So let's consider for number 1 here, so it's proof of 1, we're going to consider V1 and V2 that are in Rn. So inputs for L1. For L1. Then what we're going to ask is what happens, yeah, so we have to think about this. Our transform is this whole package here, L2 of L1 of V. So let's look at that. Look at L2 of L1 of V1 plus V2. And our goal is to show that that's equal to L2 of L1 of V1 plus L2 of L1 of V2. A little more room. That would be true if this function L2 following L1 is linear. Let me just pause there for a sec. We don't know this is true, but that's our goal. Let's see if we can tease that out using, the properties of linearity. So I seem to want to break this whole thing into a plus I wish I could break this into two separate terms. What do we know about L1? It's linear. That means that this rule up here applies. So we can break this down in one step to L1 of V1 plus L2 of V2. And that's because L1 is linear. Oh, wait, let's do that twice. Oh, sorry, this is L1 of V1, sorry. These are both things that are in the Rm. These are both in Rm, and these are inputs to L2. They're perfectly reasonable things that go into our second transform. And what about them? Well, they're just vectors that we're allowed to run through L2, but L2 is linear too. So if I have a plus inside, I can do it there, or I can break it up into pieces and get L2 of that vector, which is L1 of V1, plus L2 of L1 of V2, because L2 is linear. And that is what our goal was. We wanted to show we could break that sum of vectors in the middle into a sum of vectors after the transform was fully completed on each one separately. Usually the linearity ones are pretty straightforward, especially if it's sort of the abstract ones. There's not a lot happening. We basically rely on the linearity here of each individual function, and we just keep expanding things out. Not a lot happening. And the second part works about the same way as I could expect. So we are going to consider here an alpha that's real and a v that's in Rn. And we're going to look at L2 of L1 of alpha v. And our goal is to bring that alpha out front. Is to show that that's alpha L2 of L1 of v. I think you can see where this one's going. If each of these functions are linear, we're going to be able to bring out that alpha one at a time, one function at a time. Because L1's linear, I can bring the alpha out front of it. So I can do L2 of alpha L1 of v, trying to break up the pieces here, make it obvious what we're doing. Because L1 is linear. And then we can just do that again and get alpha L2 of L1 of v, because L2 is linear. And we're done. Ta-da. So if L1 and L2 are linear transforms, so too is L2 following L1, or if you like, yeah, let's do that. All right. And that gets us to where we want to go next with matrix multiplication. Because, just going back to that rotation example for a brief moment, if I could find a matrix that does this transformation and a matrix that does the rotation around the z-axis, I should be able to put those together because that's a combined transform, also linear. It should have a matrix version as well. And that is what we're going to get to. Matrix representation of linear transformations. All right. So we've seen this before, but just a quick reminder. We had these standard matrices for the transforms. Remember that the number of columns is equal to the number of input dimensions. Why is that? Because they are L of 1, 0, and in this case here, L of 0, 1. In there. The columns are what you get when you transform the archetypal basis vectors for your input space. If there's only two columns, that means there was only two basis vectors to work with. The output values are in the columns. So the number of rows, it's the length of each column, which is the number of rows. The number of rows is equal to the output dimension. Okay. And so that means that our transform represented here by the matrix B, let's write this out actually, LB maps from 4 dimensions, R4, to the number of rows, which is R3, while the first one up here, first transform mapped from R2 to R4. 2 columns, input was 2-dimensional, 4 rows, output 4-dimensional. And then this one had 4 columns, so input dimension 4, 3 rows, output dimension 3. With each one of these things being part of the spanning set of the image, all those other good ideas. All right. What we want to do is summarize this transformation. I want to apply transform A and then apply transform B. And I have to do it in that order because the only way for these to work is that the input from A is 2-dimensional. So we're going to go from R2 through LA to R4. And then the second transform starts at R4. We use LB, and it's going to map to R3. So only that sequence works. I can't go B first and then A. The dimensions wouldn't work out. However, I can then see what the matrix of LB following LA is, which is, we're going to call it transform C. It's going to be from R2 to R3. That maps from R2 all the way to R3 at the end in one step. And that means our C matrix has to have 3 rows. Get this right yet. 3 rows, and it has 2-dimensional inputs. It has to have 2 columns. So just how do the pieces fit together here? That's all this is. We have this A matrix, we have this B matrix. I know I should somehow be able to combine them so that I can go straight from here to here with some new alternative one-step process. And it should be a 2x3 matrix to do that. That's a lot of dimensions, a lot of sketches. Please, yeah.
2 columns, 3 rows.
2 columns and 3 rows.
Okay, because usually isn't it row like 2 by 3 usually mean 2 rows, 3 columns?
Second, I guess myself here. Damn it, yes, damn it. Erase everything I just said. Thank you for catching that early. I had a mental blank there. Yes, it's rows by columns. I was thinking about input and output dimensions, and they're in the opposite order, which is incredibly annoying. Thank you for that. Yes, so how many rows and how many columns? That's a standard something by something for matrices. And so the number of rows is the number of output dimensions. That's 3 by 2. Thank you. Oh. It's one of these, like, electrons are negative, so but flow in circuits goes from positive to negative. It's always one of the annoying flipping of things. I apologize for any confusion of that. Yeah. Number of rows is the number of output dimensions, and number of columns is the number of input dimensions. Dimensions, and that's the number of output dimensions. It's the opposite of what I expect, obviously, dimensions. All right. All right, how would we actually build this matrix, though? So what we're going to do is go back to our foundations. Hey, how do we build any transform matrix? Well, we transform the input vectors, 1, 0, and 0, 1. That's how we get standard matrices. So if we're going to build LB of LA of 1, 0, what we're going to do is we're going to transform first our 2, 3, 1, 1, 0, 1, 5, 2, and we're going to multiply that by the 1, 0 vector. And we do this sort of dot product-y thing here. We dot product the rows by column. So 2, 3 by 1, 0. 2 times 1, 3, 0, that's going to be 2. So we're going to get LB of 2. 2, and then 1 times 1 is 0, that's 1. And then 0, 0, and 5, 2. Hold on. Can anyone see a short way to get that answer without having to do those row by column dot products. Yeah. Just take everything first column, but yeah, exactly. Take that first column, that is the transform. Because what does 1, 0 do? Well, it keeps the first element and multiplies the second element by 0. So this is just the first column. So we can just copy the first column. All right, and then we do LB of that. That's going to give us something a little more complicated this time. We take our whole B matrix, 2, -1, 5, 1, 0, 4, 1, 3, -3, 0, 1, 1, and we're going to multiply that by 2, 1, 0, 5. Now that's going to be a little bit hairier for sure. I'm going to make a little more space for myself. I apologize. There we go. But notice the dimensions work. I can do, again, the product of this row and then with this column. And just as a quick note, in practice, what I usually call this is the finger following method. We're going to scale it up momentarily. It really, when I'm struggling with this and doing it by hand, I actually do follow my finger. So I actually put finger on both points here and I say 2 times 2, 4, -1, 3, 0, plus 5. 3 plus 5 is 8. So that way I don't lose track of where I am. And it seems silly. Computers can do this better than us, obviously, but if you have a matrix on a midterm or a final exam, this is how I do it. 2 times 0, 4, plus 0, plus 15 is 19. And then the last row, -6, plus 5 is -1. That's how I do it. Not sure why it's cutting out on the other side there. Give me 1 sec. That's weird. It's just twitchy. Okay. That's how we do it. But that's only half the problem because we've transformed only, so far, the first 1, 0 vector. But we actually have a shortcut we can do now, knowing what we know. If I want to find the transform of the transform of the 0, 1 vector, based on what we saw in the previous slide, when I transformed 1, 0, I just got the first column of my A matrix. That's all that was there. I look back at my A matrix, I just got that because I was multiplying by 1, 0. When we do 0, 1, guess what's going to happen? We're going to get the second column instead. So this is the same, we can do a shortcut, as the transform of the second column of A. I can jump straight to that. 3, 1, 1, 2. Because we have this 1 in the second position, we're going to have this from the second column of A. That's a bit faster. And then we can put in our actual matrix and see what we get. Yeah, you can see that right. All right. Let me zoom out of here. There. So 2, -1, 5, 1, 0, 4, 1, 3, 0, -3, 0, 1, 1. We take that and we multiply it by our 3, 1, 1, 2. And then we do the finger following thing. All right, so dot products rows against columns, dot product from here against this. 6 minus 1 is 5, plus 5 is 10, plus 2 is 12. 0, 4, plus 1 is 5, plus 6 is 11. Minus 9, plus 1 is -8, plus 2 is -6. And we are done with the finger following. So, all right, let me just pause there. Any questions about that computation? Feeling comfortable executing it?
So we can do the center matrix of B multiply like LB of 1, 0, 0, 1. But we can't, can we write it the other way? Like can we do like LB of 1, 0 matrix multiply center matrix of B?
Ask me afterwards. I'm not quite sure I understand the question.
Matrix multiplication commutative.
Oh, so that's thank you. That's a more clear statement of it. Is this matrix multiplication commutative? It cannot be, in general, because the only order that makes sense here is B following A. If we tried it the other way, if we tried to do LB first, we'd be starting off with 4 dimensions. LB gives us 3 dimensions back, and then I try to apply LA there, that doesn't work because it has to have a two-dimensional input. So we, generally speaking, cannot reverse the order because the dimensions don't work out in general. There are sometimes special cases, but rare. In general, you can't swap the order. Alrighty, that's not quite done yet because we have to put this together. The full standard matrix for C, which is equal to the composition of B and A, is going to be matrix, those two columns. So what did we get? We had 8, 19, negative 1, 19, negative 1, and then the 12, 11, minus 6. And notice that is, now they have dimensions right, that's a 3 by 2 matrix as predicted, as we wanted, as we desired. And it does both of the transformations from R2 to start with, through LA to R4, and then through LB to 3 dimensions. This matrix C here, LC, does that all in one step. So a very powerful technique for condensing a bunch of transformations together, and it has the same form as what we started with. It doesn't get any more complicated. It's still just a matrix that we're working with as our building block. And what we'd like to do is take this one step further. Hey, what we did there actually was just the same process twice. And anytime we do the same process twice, we'd like to be able to make it more general. What we did was we took the columns of the first matrix, A, and we just stuck them beside the matrix B and did scalar products. We can do that in general. There's a little blurb here, but yeah, basically what we did was we took B times each of the columns of C. That's not the most interesting part. Let's get to the actual doing it. Here's what we actually do in practice. If we want the matrix B times A, we just do it all at once. And it's going to do the standard matrix construction that we just did a second ago. It's a little hairy the first couple times you do it, but then it gets easier. Just out of curiosity, how many people have done matrix multiplication before? Like almost nobody. Okay, like 2 of you. Fantastic. All right, new for everybody. Love it. So let's do this. All right, make sure we can see that. Perfect. So if we're going to do the transform of B follows the transform of A, it's going to have a matrix that is literally what we call B times A. This is B times A with, how many multiplication operators have you learned this here? Dot product, cross product, scalar product. Now we're adding another one. We're adding the matrix multiplication, the matrix product. So it's a new kind of multiplication. It has things in common with regular multiplication that you know and love, but slightly new, slight variations. And all it is what we just did. We're going to do row by column dot products. Row by column dot products. All right. And it's a little trickier because what happens is we store things. This one I'm going to do in gory detail just to see how the pieces fall out. And then we'll do the finger following method, which is the actual practical way you do it, say on a test. To figure out what goes in this first column, we take the rows of the first matrix, and we dot them with the first column of A. That's what we did last time, right? We took 301 dotted with 301, and we dotted it with 2, negative 1, negative 3. And then we did the second row, negative 1, 2, 1, and we dotted it with 2, negative 1, negative 3. And then the other ones, we took the same row, 301, and we dotted that with the second column, 3, 2, negative 4. Negative 1, 2, 1, 3, 2, 4. So we're building a 2 by 2 matrix, fair enough. What goes into each cell? If I want to know what's in the first row and first column, so the first row and first column, it's equal to the dot product of first row of B dotted with the first column of A. And that's the same pattern throughout. If I wanted to do the one down here, if I want need the second row element in the first column, that's equal to the second row, sorry, second row of B dotted with the first column of A, sorry. Honestly, once you do 5 of them, it becomes muscle memory. The first time's really awkward, so we'll work through it. All right, when we do this, now we can do that finger following method and see what we get. We're going to get 6, 0, plus 3. Sorry, should be a negative in here somewhere that I missed. 3, 0, 1, 2, minus 3. Oh, minus 3. That's a negative. There we go. So if we do this pattern, we're going to get 6 minus 3 is 3. I go over to the next cell here, doesn't matter which way you go. 3, 9 plus 4 is 13. And then over here, another dot product, minus 2, minus 4, minus 3 is minus 7. And then last but not least, minus 3 plus 4 is 1, plus 4 is, sorry, minus 3 plus 4 is 1, plus, oh yeah, 5. Yeah. Perfect. And that checks out with the answer pre-calculated. All right. Let's do one more, just to reinforce the idea. This time I'll just do it exactly as I would do it in practice. First off, set the dimensions. The number of rows we started with is the number of rows we're going to end up with. So it's going to be a 2 by, in this case here, 4 matrix. And we just do a bunch of dot products. I'm going to take 2, 1 times 2, 1. That's going to be 4, 5. Then, sorry, 3 by. What am I saying? 3 by. Then I do the next row against the first column, negative 2 and 0. And then the next row is going to be negative 4 minus another one. It's going to be minus 5. Pause there. Then we move on to the second column in this matrix. That'll give us the second column in our output matrix, and we just go row by row. So 2 times 3 is 6, plus 2 is 8. Next row, negative 1, so that's negative 3. And then negative 6 plus 2 is negative 4. And keep repeating. Next column. So I can do the next column. It gives me the third column in the output matrix. 2 plus minus 1 is 1. Minus 1. Minus 2 minus 1 is minus 3. And then we do the fourth column. Use that whole vector, dotted product with the other ones. We're going to get 4 plus 4 is 8. Minus 2 and 0, minus 2. And minus 4 plus 4 is 0. And hopefully that matches what the correct answer was. Oh, there's a negative 1. My apologies. 3 minus 2. Everything else looks correct. Whew, okay. So in your web work, of course, there'll be practice problems for this. Also in the practice problem PDFs. Basically practice this a bunch of times, get used to that muscle memory, and we'll be using it multiple times between now and the end of the course. Thank you very much. We'll see some of you at the session tonight class tonight, and then exam this evening.